All right, Cyber Patriots, welcome back. Let's talk about some introduction to switching content as we continue learning through Cisco's Networking Academy. Course overview stuff. Going to talk a little bit about, this is actually chapter 0. Okay, first chapter, Intro to Switch Networks in this module. They got some introductory material here, nothing too technical. Read that over, get you ready for the ideas of switch networks. MAC addresses, we need to go into a little bit of that. They don't explain that concept before they throw it at you. We'll demonstrate that just a little bit. LANs and getting into converged networks and some of that kind of content. So it's all good stuff. Sent and received instructions. So they talk about switches and what do switches do. They help your service quality, voice and video data transfer, and security. And we'll get into each of those in just a bit. Growing complexity of networks, that's kind of almost marketing type stuff. Okay, networks are getting more complex, great, thanks. Elements of a converged network, so this is where you're seeing what used to be just the data network, which had the email and the web traffic. Well, now the phone traffic is often being found on the same data network. The video traffic is found on the same data network. It means your switches have to be a little more savvy about how they segment that stuff, secure it, provide for scalability and failover, all the features they're going to need with different media going across the same cable. Here's a really busy diagram. Cisco is calling this the borderless network, and this is the idea that work doesn't happen just inside the office all the time, that we're getting to where things happen at houses. They follow you around on your mobile device using VPN to connect in from outside places. So they're calling it borderless, where you still can there's not one discrete, this is the inside of the network and this is the outside of the network. You've got the PSTN, so that's your public telephone system. The wide area network connecting a couple of sites with these routers here. Different campuses. Here's an internet edge, and then you get further into the core. Smaller campus has different blocks of switches that tier things out. So getting into this tiering thing and this getting away from this notion of the castle with the moat and everything's either inside or outside. So they're working that way. Also helps them sell a lot more stuff, which that's what this is. This is a Cisco's license to print money slide here, because instead of having a couple of devices managing all your network traffic, now they want to give you resiliency and redundancy. So you got to buy 2 of everything of these expensive devices, and you've got to put it in these 3 and 4 layer stacks. But honestly, it is architecturally sound. So you've got the internet on the very extreme outside on the top of the diagram. Down here, you've got the user PCs and their phones. And so those things all, your phone and your PC, those things connect to switches that are out at what they're calling the access layer. And there would be switches in some closet near where this batch of users is that all of their cables are going to connect in. Then go and do some more consolidated switches that they're referring to as the distribution layer. Then all of that would land in a centralized closet with some really larger switches in a core layer. Some of these might even be connected with fiber. You might have fiber from the distribution layer to the core layer, probably the copper Cat5 that we've seen, like what you see in your wall jacks. Those areas would be here. And then, of course, these things being able to be redundant. So your distribution layer, you've got 2 of them here, and everything can connect to one or the other. So if you lose this distribution layer switch, well, everything can get to the core layer with this one. If you lose one of your core layer switches, well, there's multiple paths like either of these distribution switches. It can go this way, it can go this way. This one can go this way or this way. Your core layer, it can get to whichever one of these routers that it needs to. So in the routers, of course, both of them have the internet access. And what you often will do is set these up so that they can balance the traffic between them, share all the load. But if one of them that goes down, it can fail over, might not run as fast, but you would maintain connectivity. And so you've got this dual setup, good for failover, good for performance, and good for Cisco's stock price. And so you've got these characteristics, these following principles. It's hierarchical, access layer, then the distribution layer, then the core layer, kind of as you move from the bottom to the top, or in some ways from the outside to the in is probably the better analogy. Modularity, so you can expand things. These types of switches have cards you can move in and out if you need to expand it. It's not like buy a whole new device. You move modules in and out of it if you need to expand it. Resiliency, that's where we talked about having not one single point of failure. If one device fails, something else can pick up. And flexibility, you can take these things and you can do your phone traffic, you can do your data network from your PCs and so forth. Now they're going to talk about those layers some more, the access, distribution, and core layers, which touched on that some. Again, working outside in. This diagram shows that a little bit more as an outside in analogy as opposed to a top to bottom. Okay, now I've got switch network terminology. Check that out. Just click each one, do your check, back up a couple slides if you need to check your learning. More on hierarchical switch networks. Really, honestly, I think somewhat redundant. But again, you've got your layers. They've separated the three without labeling them, though, of the core and your distribution, and out further to the client side with the switches and the end user devices here. Form factors, that's physical design. You can get switches of all kinds of sizes and capacities, and you'll hear them use a comment called a 1U, a 1 unit, or 1U. So that if you slide one of these into and we'll see a picture of one of these, if you slide one of these into a frame, it would take up 1U. That's like the smallest height that one of these could take. We'll see that in one of the diagrams here in a second, all the way up to things that are much, much larger and are entire cabinet sized. Considerations are cost, port density, how thick on one thing do you get, the Wi-Fi router you have that's got maybe 4 ports, that's not a huge port density. In a large corporate environment, you get these things that are 24 and 48 port switches on just one switch. High port density, but sometimes you need that. Power, you have switches that can actually be the source of power for a telephone. When you use the voice over IP, that's pretty common now. You'll see PoE or power over Ethernet. You would plug your phone into the jack on the wall like we've talked about, and it can draw its power from the switch port that's on the other end of the cable. Reliability, so that gets back to having the pairs of devices so that there's failover. If one dies, the other can pick it up. Port speed, how fast does it go? We've got anywhere from 10 gig to 100 gig to meg and so forth. And frame buffers, and they'll get more into the frame design stuff in a little bit on how the size and design of the frames as they go across the network and what the switch does, if it stores them or if it passes them along immediately. And the number of users, you have a whole lot of folks in a certain area, you might need to add some capacity. How hard is that to do within your design? Okay, and then kind of review which one of these goes which one of the items to match up with. Good exercise. Work on that one. Back up a slide if you need to review any. And then a little video talks about, we'll touch on this video a little bit. So we've got this LAN switch. It's got a destination. Let me pause it there. It's got a destination address of EA. That's an abbreviation of the MAC address, which we'll talk about in a second. I'll demo that on my machine. A destination address of EA. So it's on the other end of, this is one of those cables like we've seen on a switch. On the other end of that, that plugs through a wire, hits another jack that goes through the wall. Then you trace it all the way through the wall, and that would end up on a port on the wall where there's a wire plugged into your PC. So it's your computer through a little cable we call a patch cable. That plugs into the wall. Then you could trace the cable through the wall to the other end where this switch is, another patch cable, and it lands right here on port number 1 of this switch that we're looking at. So the destination address is EA. So it comes in off of a computer to this first port, and it's looking to send it out whichever one of these other ports has the computer that is address EA. So we look through, and there's EA right there. It's on port 4, so we should see it pop it up on port 4 because that's where the location of the PC is. That's the destination of this email or whatever kind of traffic. All right. Port EE, that's here, so we should hopefully see that pop out on port 1. And then 1 comes in on port 3, goes to AB. That's going to go out on whatever device is at port 6 that has a destination address of AB. All right, simple idea. Now, let's break off just a bit and let me open up a command prompt. And let's talk about this MAC address business, if we can. Do I have to do an ARP? I think I'll have to do an ARP. Okay, here is an example. So an ARP is ARPing is to get something called a MAC address. So we've talked about IP addresses, like there's an example IP address right there, and we've seen all this business about public and private IP addresses, and those are numbers that get assigned, and it's important to say assigned because that means they're not permanent, to a device on the network, like my laptop right here. And so my laptop has an IP address. It's probably still sitting on 192.168.10.1.10, I think it was, and it's got that IP address that my Wi-Fi router is assigning out. But that IP address could change. I could get a different IP address later. I could hard code one, like we talked about. What's different is that my PC has a MAC address, and they look like this. They're hexadecimal, so they could go from 0, each space, each position could be as low as a 0 and as high as an F. So it goes 0 through 9. Then instead of thinking of a 10, it goes to an A, B, C, D, E, F, hexadecimal numerical notation, base 16 numbers. And so you could go 0 through 0 to F on each of these digits. And that is something that's hard coded. So my particular computer, its network address, its network card, or the chip that acts like a network card, it has a number just like this. And the network card you're using has a number like that. And it's not something that's assigned over the network like an IP address is. That MAC address is permanent. There's ways you can fake that and do some network tricks to manipulate, but essentially it's always permanent. And they keep these straight because there's conventions I can't remember specifically, but you can look these up where a certain vendor has numbers that are 00AA00, and that would be the prefix for all Cisco devices or all devices from Dell computers or what have you. And they are given a prefix, and then within theirs, they're allowed to say, okay, different model numbers get a certain thing within. So like, let's say 00AA and 00, if that was Dell's MAC address range, for example. And then 62, it could be 00 through FF, are things they can do for different model numbers. And then for that model number from like Dell's this part, that model number, then they can go through 00 through FF for the other 4 digits for the specific ones that they produce. So idea being, though, that each computer, each device gets a unique MAC address that's essentially permanently assigned. So when you see the switch moving this stuff around, where it's got this table to remember this stuff, it's remembering that permanent address that's attached to, associated with the network device that you're using. So there's an EE. Instead, they're saying an EE to abbreviate. It actually would be the longer number, like what we were just looking at. That set of doubled up set of 6 numbers, and that's what would be assigned within the switch's memory on port 1, and it would know that. Once something's transmitted and it figured out where did you come from, oh, okay, let me write your MAC address down, and it writes them down as it learns them, and it talks about what happens on the learning process first. Okay, dynamically populating. So we start out with this PC, and it's got a MAC address. It's got an assigned temporary IP address, but more importantly for now, it's got this permanent MAC address. And it's going to send some data, and it's going to hit a switch port, 1 through whatever switch port that it's physically plugged into. And when it does that, it's going to say, I'm MAC address for PC1, so the switch gets to populate whatever this MAC address was. So it knows from now on, the port that was here is PC1. So if something ever tries to send to PC1, it knows how to find it because it says, oh yeah, you're on port number 1 of the switch. And it's going to say, now I want to send this to another device. Well, the switch doesn't know the rest of these yet, so it sends it to all of them. Says, here, everybody, I've got something that's destined for somebody. I don't know who yet because I don't have all of my ports populated. All I know is that port 1 is PC1, and PC1's the sender, so he's not sending it to himself. So which one of you guys is this? Then you get back port 3, it says, hey, that's me. Can I have that data? So now it says, oh, okay, you're on port 3 and you're PC3, so it kind of writes that one down. And the PC3 says, yep, that's my message. Can I please have that? And notice that it's written down in its little memory of its little table that it keeps track of. Oh, okay, so now I know it's on port 3. Doesn't know it's on port 2 yet, hasn't had occasion to do any traffic with it. And then it goes back and says, okay, this is the other address we need to talk to. So from then on, as PC1 says, hey, I need to get some message for PC3, when it hits the switch, it knows where to send it, so it'll send it directly without broadcasting it to these others. Okay, switch forwarding methods. There's store and forward, which means I'm going to wait until I've got a whole bunch of stuff, and then I'm going to push it through, versus cut through, which means it just sends it on. That's all we're going to get into on the two methodologies. There's cut through, which just, it goes faster, a little more. It can be faster to get started, but it also could be a little more error prone. There's an exercise if you do want to read it and check that, but not a level of detail I think we need to worry about right now. Collision domains. So essentially, this is where long ago you had these things that preceded switches called hubs. They were set up where everybody will try to talk on the network at once, and two devices talking across the same cable at once, well, that would cause what's known as a collision, and then you would have to retransmit. With switches, you started to mitigate that. More intelligent devices and collision domains, in a lot of ways, kind of, what do I want to say, almost eliminated the problem. Then there's broadcast domain. So you've got a switch, and it's got several devices, this switch with devices, this switch with devices. Now, broadcast is back to the idea of, I really don't know where this goes. This isn't a port that's on my directory just yet. So if I don't know, I'm going to send this to everybody. So we're going to watch this little segment. So this sends out a device, and it's sending it to everyone because it doesn't know exactly where it needs to go. This one, these two switches are connected, so it sends it to all of its devices and to its sister switch it's connected to, and it broadcasts it to these also. It doesn't know where to go. Well, any switches that are configured together, it's going to send it to all of those until it can figure out where the device is that needs to get that traffic. Okay, now here's some different scales of switches. So remember, we saw in one of our early team meetings, we saw a switch, and it was a very small 1U switch. And so if you look at these are much larger stacks of switches. So here's actually 4 of them, I think, that are, I don't think that's one chassis. I think that's 4 stacked together. And you would put these, there would be like a rack that this could sit in. And look at all the ports that you've got. So that's what we would call a much higher port density, or especially over here. We could sit and try to count all those, but that's a lot of stuff. So this is where you would probably go in some switch closet. A whole bunch of wires from all over a building converge into a patch panel, and then you would wire all of these. And each one of these ports, if you could trace it, from one of these particular ports goes through a wire that's in a wall in the switch closet, follow that through the building, it would end up on the other end of a wall somewhere in an office, and then off that one there'd be a cable that goes to a PC. So in a sense, each one of these represents a connection to a computer. And each one of these ports, if you start with number 1, number 2, number 3, and so forth, each one of those would record the MAC address of that PC that's on the other end. So if port number 1 has a certain MAC address recorded, and then port number 2 has another PC, and port number 1 and PC number 1 hits this port saying, I need to send a message over to another computer, it checks its directory, see, do I know for the message for this other computer which one of these ports that's connected to? And if it doesn't know, it's going to do what? Broadcast it till it can figure out where that belongs, and then it'll write it down for next time. Here's some more examples. You've got these other ports too, or you might have uplink ports that are higher bandwidth to connect the switches or connect upstream to another device somewhere. And these would normally be the ports that you would use for your end devices. And then that's a monster. Notice it's a whole bunch of ton of ports, probably a bunch of extra cooling in here, probably power supplies, extra pieces, fully redundant. That's a pretty hefty piece of gear right there. But in a large environment, enterprise environment, you're going to need something like that. Okay, then there's this broadcast domain. Honestly, this one gave me trouble. So when you try it a few times, but it's almost, the answer is almost too obvious if you do this exercise. So see if you can get it on the first try and beat the instructor. Then we've got, so some classroom exercise stuff. And then there is a thing of, this is a refresher on some switch typing commands. I would recommend on this, if you want to try to do the exercise and see what you can do, but at least just do show me and work your way through each of those. And then if you want to, you get some time, reset it and see if you can follow through the whole exercise. That's pretty good. We'll be getting into a lot of that after round 1 competition. And then here's the packet tracer skills integration challenge. So we see that we're near the end. And again, we'll probably come back and do all of these as an exercise after we finish our first competition round. And that'll be a lot of fun as we start getting more into the tracer tool. And so there's the summary. And again, a big diagram. I think we already saw this exact diagram, with the PSTN and the WAN connections. So they're just trying to get the ideas. We'll see a little more detail in the next switch class, but they're showing the idea of how they store and forward, or how they get traffic back and forth. Key idea too about saving those MAC addresses in a little table that it keeps to remember how to forward those next time. That's probably maybe the most important idea. Plus also the broadcast domain business. That bit of logic's probably the key thing to pull out of this, along with just the idea of what a MAC address is and so forth. So not a real long chapter, not too in depth, but some good baseline stuff so we can move forward, and then we'll get some more in depth into switching on the next one. We'll see you soon. Thanks.